All right, ladies. So we are starting section 3.2. You have the handouts because hopefully I passed them out in class. And so this is going to be one probably of two videos to complete the notes. All right, let's get started. So first, some definitions. Let A be a set and R be a relation on A. Okay. R is reflexive. R is reflexive on A if and only if for all X belonging to A, X relates X. Okay. R is symmetric if and only if for all X, Y belonging to A, if X relates Y, then Y relates X. Okay. And then R is transitive if and only if for all X, Y, and Z in A, if X relates Y and Y relates Z, then X relates Z. Okay, and so just note here, to prove that a relation R is symmetric or transitive, we usually use a direct proof, since these properties are defined by conditional statements. As you can see, the if, then, which you know how to set up any proof that has if, then. A proof that R is reflexive on A is different. You must show for all X belonging to A that X relates itself. And you would think it's straightforward, right, to show that something relates itself. However, reflexive property, when we get into proofs, can sometimes be the hardest to prove because it's so obvious. But you can't really just say it's obvious. You have to sort of go a roundabout way. So just keep that in mind. All right, negations of the three properties above. You all should remember, similar to when we were negating it's still quantifiers here and conditional statements. So a for all negation would be what? There exists, right? So there exists an X such that X does not relate. So we put that line through there, X. Okay, and so proof notation, because you know how the structure for there exists, quantifiers and things of that nature in conditional statements. There exists an X belonging to A such that X does not relate X. Okay. And then for if P then Q negation, remember it's P and not Q, right? So this is equivalent to X relates Y and Y does not relate X. Okay. And so in terms of how you would set up in your proof structure, the notation would be there exists an X and Y belonging to A such that X relates Y and Y does not relate X. Okay. And then the negation of the transitive property is still similar because it's a conditional statement. So you would say X relates Y and Y relates Z and X does not relate Z. Okay. And so that would look like there exists an XY belonging to A. Oh, I'm sorry, I forgot about Z. X, Y, and Z belonging to A such that X relates Y and Y relates Z and X does not relate Z. Okay, so and sometimes in videos I'll write stuff, and so you can just pause the video and write in what I have so far and then follow along. Here in example 1, for each example below, list which of the three properties, reflexive, symmetric, or transitive, hold. So I just want to, before we start doing proofs with these, I want you to get comfortable with understanding them and looking at sets and determining which properties hold. So let's look at reflexive. So there's two sets. Well, S and T are relations on B. So there's two relations we look at. We'll look at them one at a time. So let's look at our S relation. Okay. So the question is it reflexive? Okay. Well, we don't see the definition going back to reflexive. It's saying R is reflexive on A if and only if for all X in A, X relates X. So for all X in A. So this is our set B. We have 2, 5, 6, and 7, right? So that means 2 should go to 2, 5 should go to 5, 6 should go to 6, and 7 should go to 7. So it is not reflexive, right? Because the only thing going to itself is 7, but by our definition of reflexive, if it's in that set, it needs to reflect itself. Or relate to itself, I should say. All right, so it's not reflexive. Is T reflexive? No, right? That's not reflexive either. All right, let's talk about symmetric. Now, symmetric is conditional, right? So it's saying if something is in there, then if X relates Y, then Y must relate X, right? And so if it's not, if you can't set up that if statement, then a false is true, right? So just be careful there, and we'll talk a little bit about that when we get to transitive. So let's look here at symmetric. So meaning 2 relates 5, right? But 5 doesn't relate 2. So this is clearly not reflexive. And then for T, 2 relates 6, but 6 doesn't relate anything. So that's all. I'm sorry, not reflexive. We've moved on from that. You guys caught that in the video? Very good. Thank you for mentioning that. And it's not symmetric. All right, so S and T are neither symmetric. What about transitive? So now the transitive property, if you need to pause it, or you might not have to pause, just look back over on the first page. If X relates Y and Y relates Z, then X relates Z. So you first need to be able to set up that if condition, if X relates Y and Y relates Z. So looking at, let's go to T, because T, can you set up the if statement here? 2 relates 6, but 6 doesn't go anywhere. And then 5 relates 6, but 6 is not in there. So you cannot set up that condition. Because you cannot set it up, then a false is going to yield a true statement. So it is transitive. Okay. And you might have to think about that for a minute, because it's important to understand why it is transitive, because you have to be able to set up that if condition. And then let's look over here. Well, 2 relates 5 and 5 relates 6. Oh, 2 does relate 6, right? So that transitive property works. So that actually is in there. What about, let's see, 5 relates 6, and you can't set up anything after that. 2 relates 6, but again, you can't set up the second part. And then 7 relates 7, but you can't set up the second part. So this is transitive because the only if you can set up is the 2 relates 5 and 5 relates 6, which will yield a 2 relates 6, which is in there. So that is transitive as well. So the first one is transitive because we see that all the combinations where you can set up the if statement, it actually is true that then statement is in there. But the T, this relation is transitive because you can't set it up, right? And so false for you can't set it up, which is false, and then false for the then statement, and that's going to yield our true. Okay, so hopefully that made sense. Okay, so let's look at our next example. Let R be the relation is a subset of. So this here is defining what the relation is. Okay, we're not given a definite set like in A, but we're given what it's defining. So is a subset of on the power set of Z, and the power set of Z. Okay, P of Z, which is the power set of Z. Okay, so let's think about this. Remember, we're talking about the power set. So something is a subset of on the power set of Z. So that means we're talking about sets, right? Our elements are sets. So this first one, the reflexive property, if we think about the definition, this one would say for all S, and S is just some set belonging to the power set of Z, S relates S. S is a subset of S. Well, that's true, right? Because every subset is a subset of itself, okay? So since every subset is a subset of itself, then it is actually reflexive. So this is reflexive, this relation. Okay. What about symmetric? So if S relates, so I guess if you're thinking about it in terms of for all ST belonging to the power set of Z, if S relates T, then T relates S. So pause and see if you can just think of a set to determine. Just pick a set and pick a set that's a subset of it, or pick a set and see, can you solve this and figure out if this is true or not. So just pause it for a minute and think about what this question is asking. Okay, I hope you figured out that this is not symmetric. And an example I could just look at is something simple. So we can see here that the set containing 1, 2 is clearly a subset of the set containing 1, 2, 3, right? Because this is a subset of, right? And we're on the power set of the integers, all right? So we're just looking at sort of our integers. And so that's obviously true, right? We know that's true. But the subset 1, 2, 3, the set containing 1, 2, 3 is not a subset of 1, 2. So it is not symmetric. Okay. For the transitive property, we actually can recall a theorem to help us answer this question, because recall page, I put page 73, but that was in the old book. So it's actually page 88 in your book. And theorem 2.11c. Okay. And it says if A is a subset of B and B is a subset of C, then A is a subset of C. Okay. And so that's what the relation is asking for. And so this is true. But just to look at an example, we can say, well, if 1, 2, the set containing 1, 2 is a subset of 1, 2, 3, and 1, 2, 3 is a subset of 1, 2, 3, 4, then clearly 1, 2 is going to be a subset of 1, 2, 3, 4. Okay. And so if you wanted, you could prove that. That's a pretty straightforward proof. So it is transitive. Okay. So next we're going to look at this, and we have a relation. So let B be the relation XY belongs to Z cross Z, such that X times Y is greater than 0 on Z. Okay. And so let's think about, well, is it reflexive? Well, we're on the integers, right? So that means, so think about it for a minute. Is it reflexive? Well, what about when X is 0? Okay, because that's an integer, right? 0 is an integer. And so if X is 0, then let's see. So this is asking, does X relate X, which would mean 0 times 0. So does 0 relate 0 in this relation? Well, that would be 0 times 0, which is equal to 0. And of course, that's not greater than 0. So it's not reflexive. Okay. So it only, remember, it's a for all statement. So if there is 1 to disprove a for all you have to show that there exists 1 that makes it false. And so it's not reflexive. Take a minute and think about the other two and then come back to the video. Okay. So you should realize that it is symmetric, because since this is multiplication, so since this is multiplication here, that multiplication is commutative, right? And so it is going to be reflexive, okay? And just a little mini proof that it is symmetric. Symmetric. Suppose X relates Y. Well, that means XY is greater than 0. Well, since multiplication is commutative, xy is the same as y times x, and so that's also going to be greater than 0. And so we would say thus y relates x and v is symmetric. All right, think about transitive. See if you can solve transitive and come back to the video. Okay, so as you discovered, it was transitive. Very good. And this is sort of a little mini proof. I'm missing, I think, a couple of things to make it a little more formal. We're going to do a proof on the next example. But this is what we have. So remember, transitive says if x relates y and y relates z, then x relates z. Well, suppose our if statement, x relates y and y relates z. Well, that means x times y is greater than 0 and y times z is greater than 0. Okay. We have to show that x times z is greater than 0. Well, since y is contained in both those inequalities, then y could either be positive or negative, right? Well, if y is greater than 0, then x has to be greater than 0 and z has to be greater than 0. Thus, x times z is going to be greater than 0, and this would and this relates to x relating. This, I want you to see that x relates z, right? Well, what if y is less than 0? Well, then x has to be less than 0 and z has to be less than 0. And therefore, x times z will be greater than 0 and x relates z. Okay, therefore, x relates z and v is transitive. So v, this relation v is symmetric and transitive, but not reflexive. Okay, ladies, so here are some digraphs. Now I want you to examine these digraphs as sort of a visual representation. I want you to draw them, the 3 examples, and then pause the video and see if you can figure out which properties hold for each of these. Now, when you unpause the video, all the answers will be there. So make sure you really, really try to pause the video first and then come back before you look. Okay, so here are the answers. I'm not even going to go over them. I want you to confirm my answers, and if there are any questions, then bring them to class. Because of time, and I need to stop at 20 minutes, so the downloading process will be okay, and it'll upload to YouTube fine. I want to go to the last of part 1, so we're stopping here on page 4 of your notes. And so we've been talking about reflexive, symmetric, and transitive. And so a set R on a set A is an equivalence relation on A if and only if R is reflexive on A, symmetric, and transitive. So we're going to show that XY belonging to Z cross Z, such the relation R equaling XY on Z cross Z, such that X plus Y is even, is an equivalence relation on Z. Okay, so I'm going to show you reflexive and symmetric in detail, and then for transitive, I'm going to have you do it on your own, although I'm going to post it on here. So reflexive. Okay, so this is what we're trying to show. For all xy belonging to Rx, x relates x, which means x plus x is even. All right, well, this is pretty straightforward, right? For all... Oh, not XY, just for all x belonging to the integers. I'm sorry, let's redo this. That was me trying to rush. This is reflexive, so it's just for all x belonging to the integers, because that's our domain for x. X relates x, okay? And so and I might go over 20 minutes, so I might have to make another short video for you to finish the proofs up. Let x relate z. I think I am going to stop here, so I won't have to stop midway in the proof. I'm going to stop here, and then you'll have another video to finish this proof.